A brilliant streak of light crossing the night sky has always commanded attention. But timing and location can transform a routine astronomical event into something far more intriguing in the public imagination. On the evening of June 14, 2026, thousands of people across a vast stretch of the United States looked upward and witnessed a dazzling fireball racing through the atmosphere above the Mississippi River region. Reports poured in from as many as 18 states. The glowing object appeared bright enough to dominate the night sky for a few fleeting moments before disappearing into darkness. Its path happened to pass over one of the most closely watched geological regions in North America, the new Madrid Seismic Zone. The coincidence was impossible for many observers to ignore. A fireball over the Mississippi River, a fault system responsible for some of the most powerful earthquakes in American history. Thousands of eyewitnesses spread across nearly half the country. Was the timing meaningful? Was it merely chance? Did the object have any connection whatsoever to the restless geology hidden beneath the central United States? Those questions emerged almost immediately as videos circulated online and reports accumulated from state after state. Available observations indicate that the fireball traveled across southeastern Missouri and was visible across a broad swath of the nation. The event generated hundreds of reports submitted to meteor tracking organizations, demonstrating just how prominent it appeared in the sky. Sightings extended far beyond the immediate region, reaching observers hundreds of miles away. The sheer number of witnesses reflected both the brightness of the object and the growing network of smartphones, security cameras, vehicle dash cameras, and dedicated sky watchers capable of documenting such events. Although the spectacle attracted widespread attention, the larger reason for public fascination lay beneath the fireball's path. The new Madrid Seismic Zone occupies a unique place in American geological history. Stretching through portions of Missouri, Arkansas, Tennessee, Kentucky, and neighboring states, the fault system is associated with the famous earthquake sequence of 1811 and 1812. Those earthquakes remain among the strongest ever recorded within the continental United States. Unlike the tectonic plate boundaries of California, where fault lines are visibly linked to the movement between major crustal plates, the New Madrid region exists deep within the interior of the North American plate. This makes it particularly fascinating and, to some observers, unsettling. Earthquakes there occur far from the plate boundaries that most people associate with seismic activity. The earthquake sequence of 1811 and 1812 was extraordinary in both scale and geographic reach. Historical accounts describe church bells ringing hundreds of miles away, ground fissures opening across the landscape, and powerful shaking that affected an enormous area. The Mississippi River itself reportedly experienced dramatic disturbances, including temporary reversals of flow in certain locations due to earthquake-generated waves and ground deformation. Those events became embedded in American geological memory and continue to shape perceptions of seismic risk in the central United States. As a result, nearly any unusual event occurring above or near the region often sparks speculation. The June 14th fireball was no exception. Social media quickly filled with questions linking the meteor to the fault zone below. Some wondered whether the object represented a warning sign. Others asked whether impacts from space could somehow trigger earthquakes. A smaller group suggested that unusual celestial events historically appeared before major geological disasters. Such ideas are understandable from a human perspective. People naturally seek patterns, especially when confronted by dramatic events. Yet the available evidence surrounding both meteors and earthquakes points in a very different direction. A fireball is essentially an exceptionally bright meteor. These objects are typically fragments of rock or metal entering Earth's atmosphere at tremendous speeds. As they plunge through increasingly dense layers of air, friction and compression heat the surrounding gases, creating an intense glow visible across great distances. Depending on the object's size, composition, velocity, and angle of entry, the resulting display can range from a brief streak to a spectacular fireball capable of outshining planets and even the moon. Fireballs are much less common than ordinary meteors, but are far from rare on a planetary scale. Astronomical organizations receive reports of such events regularly. Many occur over oceans, remote regions, or during daylight hours when they go unnoticed. Modern observation networks reveal that bright fireballs occur far more frequently than many people realize. The June 14th event appears to fit comfortably within this category. Reports collected from observers indicated a trajectory passing over southeastern Missouri, placing the object within the broader Mississippi River corridor. The American Meteor Society received hundreds of eyewitness accounts, demonstrating the extent of its visibility. Some observers described an intensely bright object crossing the sky before fading from view. Others reported a brief flash illuminating the surrounding landscape. At first glance, the coincidence between a fireball and a major fault zone may appear remarkable. Yet a closer examination reveals that the overlap is less extraordinary than it initially seems. The Mississippi River Valley covers a vast geographic area. Millions of people live throughout the region. Numerous highways, cities, towns, farms, and transportation corridors occupy the landscape. The new Madrid Seismic Zone itself extends across hundreds of miles. When a bright meteor becomes visible across multiple states, the odds increase significantly that it will pass over some notable landmark, city, river, or geological feature. In other words, the apparent connection largely emerges from geography and scale. The sky visible above the central United States covers an immense area. A meteor crossing hundreds of miles of atmosphere can appear over countless locations simultaneously. The fact that one passed above a region containing a famous fault system does not automatically imply a relationship between the two phenomena. Scientific understanding of earthquakes provides additional perspective. Earthquakes occur when accumulated stress within Earth's crust exceeds the strength of rocks along a fault. Over time, strain builds due to geological processes operating across immense timescales. Eventually, rocks fracture or slip, releasing stored energy in the form of seismic waves. A meteor entering the atmosphere operates within an entirely different physical system. Most fireballs never reach the ground intact. Many disintegrate high above Earth's surface. Even when fragments survive, the energy involved is generally concentrated in the atmosphere rather than transferred efficiently into the crust below. The atmospheric flash, sonic effects, and visual spectacle can be dramatic, but they rarely exert meaningful influence on deeply buried fault systems. Historical records support this distinction. Human civilization has documented meteors, comets, and earthquakes for thousands of years. Occasionally the two occur close together in time, generating speculation. Yet extensive scientific study has not established a consistent causal relationship between ordinary meteor events and major earthquakes. The overwhelming majority of earthquakes occur without accompanying celestial displays. Likewise, countless meteors streak across the atmosphere without triggering seismic activity. This does not mean impacts can never affect Earth. Large asteroid impacts represent a completely different category of event. A sufficiently massive impactor striking the surface would indeed generate seismic waves. Geological evidence demonstrates that ancient impacts have reshaped landscapes and affected global environments. However, those events involve objects vastly larger than the typical fireballs observed in modern skies. The June 14th fireball belongs to the latter category rather than the former. Current observations suggest a bright atmospheric event witnessed across a wide region, not a catastrophic impact. No evidence has emerged indicating a major collision with the ground capable of influencing regional tectonics. Reports instead align with the normal characteristics of a bright meteor passing through the atmosphere. Even so, the event offers an opportunity to examine why the new Madrid region continues to attract such attention. Unlike California's famous fault systems, the new Madrid Seismic Zone occupies a setting that remains the subject of ongoing geological study. The region lies within an ancient structural weakness in the North American crust known as the Reelfoot Rift. This failed rift system formed hundreds of millions of years ago during an unsuccessful attempt to split the continent apart. Although the rifting process never progressed to the creation of a new ocean basin, the crust retained inherited weaknesses. Many researchers believe these ancient structures continue to influence modern seismic activity. The result is a fault system capable of producing significant earthquakes, despite its location far from active plate boundaries. This unusual setting contributes to public concern because seismic waves travel differently through the central and eastern United States than they do in many western regions. Older, colder crust can transmit earthquake energy across greater distances. Consequently, moderate and strong earthquakes in the New Madrid region may be felt across exceptionally large areas. That reality helps explain why memories of the 1811 and 1812 earthquakes remain so powerful. The historical events were experienced across a substantial portion of the young United States. Reports described shaking extending far beyond the immediate epicentral area. Modern seismic hazard assessments continue to account for the possibility of future significant earthquakes within the region. Yet acknowledging that risk differs greatly from assuming that every unusual event represents a warning sign. Throughout history, people have associated earthquakes with eclipses, comets, planetary alignments, unusual weather, animal behavior, and countless other phenomena. Most of these perceived relationships emerged because humans are exceptionally skilled at noticing coincidences, while often overlooking the vast number of instances where no connection exists. The June 14th fireball illustrates this tendency perfectly. A spectacular object crossed the sky above a famous fault zone. The coincidence is memorable precisely because the fault carries historical significance. Had the same meteor passed above an area lacking a well-known geological feature, public discussion would likely have focused exclusively on astronomy rather than earthquakes. The modern era amplifies this effect. Within minutes of a fireball appearance, videos can circulate across social media platforms. Maps of fault systems are readily available online. Historical earthquake accounts can be accessed instantly. As information spreads, separate topics become linked in public conversations, sometimes creating the impression of a relationship where none exists. Meanwhile, the fireball itself remains scientifically valuable, regardless of any seismic speculation. Every bright meteor provides researchers with opportunities to better understand the small bodies populating the solar system. Meteoroids represent fragments left over from planetary formation processes that occurred billions of years ago. Studying their trajectories, compositions, and behavior during atmospheric entry helps scientists reconstruct aspects of solar system history. Observation networks have become increasingly sophisticated in recent years. Ground-based camera systems, satellite sensors, radar observations, and public reporting databases now allow researchers to reconstruct meteor paths with remarkable precision. Some events are tracked from atmospheric entry through fragmentation and, in rare cases, to the recovery of surviving meteorites. These advances mean that modern fireballs are often documented far more thoroughly than similar events from previous generations. A bright meteor that might once have been witnessed by only a handful of people can now be recorded by hundreds of cameras. This increased visibility can create the impression that fireballs are becoming more common, when, in reality, observation capabilities have improved dramatically. The June 14th event exemplifies this transformation. Hundreds of reports arrived from observers across numerous states, allowing organizations to estimate the object's path and visibility range. Such extensive documentation would have been impossible only a few decades ago. As attention gradually shifts from the spectacle itself toward broader questions about the new Madrid Fault, one conclusion remains firmly supported by available evidence. No verified data indicate that the fireball served as an omen, warning, trigger, or precursor for earthquake activity within the new Madrid Seismic Zone. The timing was striking. The location was noteworthy. The visual display was memorable. None of those factors, however, establish a physical connection. Earthquakes continue to be monitored through seismometers, geodetic measurements, and geological analysis. Meteors continue to be tracked through astronomical observations and atmospheric detection networks. These are distinct phenomena governed by different processes operating on vastly different scales. That distinction is important because extraordinary sights in the sky often invite extraordinary interpretations. The Mississippi River corridor has witnessed many remarkable events throughout history, from major floods and earthquakes to eclipses and meteor displays. Each carries its own scientific explanation. Sometimes they overlap geographically. Occasionally they occur close together in time. Such coincidences can be fascinating without necessarily being meaningful indicators of deeper connections. For residents living near the new Madrid Seismic Zone, the appearance of a brilliant fireball overhead served as a reminder of two powerful forces that shape human understanding of the natural world. One arrives from space, blazing across the atmosphere in a brief burst of light. The other remains hidden beneath the surface, releasing energy through movements of ancient faults that may remain quiet for years, decades, or even centuries before producing noticeable earthquakes. On June 14, 2026, those two worlds appeared to intersect above the heart of America. Thousands looked skyward and witnessed a celestial visitor crossing the darkness above a region famous for seismic history. The image was compelling enough to spark questions from coast to coast. The available facts, however, point toward a straightforward conclusion. A bright meteor crossed the sky over the Mississippi River region and became visible across a huge portion of the United States. The new Madrid Fault happened to lie beneath part of that path. The coincidence captured public attention because both subjects are dramatic in their own way. For now, the fireball stands as an astronomical event rather than a geological warning, a fleeting visitor from space that illuminated the night above one of America's most watched fault systems before disappearing as quickly as it arrived. Public fascination with the new Madrid Seismic Zone has persisted for more than 2 centuries, partly because of the rarity of large earthquakes in the central United States. In regions where earthquakes occur frequently, communities often become accustomed to regular seismic activity. California experiences thousands of earthquakes every year, most too small to cause damage. Residents understand that seismic movement is a routine part of life. The new Madrid region presents a different picture. Long periods of relative quiet are interrupted by occasional bursts of activity. This pattern creates uncertainty because human lifetimes represent only a tiny fraction of geological time. A fault may appear inactive for decades and still possess the ability to generate powerful earthquakes in the future. That reality often leads people to search for clues. Whenever unusual natural events occur near the Mississippi River Valley, speculation tends to follow. Floods, unusual weather patterns, unexplained sounds, and even astronomical events have at times been linked in public discussion to the possibility of future earthquakes. The June 14th fireball joined a long list of occurrences that attracted attention because of their proximity to the new Madrid Seismic Zone. Yet modern monitoring systems offer a much clearer picture of fault behavior than was available during the early 19th century. Hundreds of seismic instruments continuously monitor the central United States. These sensitive devices are capable of detecting earthquakes far too small for humans to feel. Every tremor contributes to a growing database that helps researchers understand patterns of stress release and fault movement throughout the region. The new Madrid Seismic Zone remains active today, although activity typically occurs at magnitudes far below those associated with destructive earthquakes. Small earthquakes are recorded regularly across portions of Missouri, Arkansas, Tennessee, Kentucky, and neighboring states. Most pass unnoticed by the public. Their existence demonstrates that the fault system is not dormant, but neither do they indicate that a major earthquake is imminent. This distinction is important because seismic systems rarely provide simple warnings. Popular culture often portrays earthquakes as events preceded by obvious signals. Reality is considerably more complicated. Scientists can identify regions where earthquakes are likely over long periods of time, but predicting the exact date and magnitude of a future earthquake remains beyond current capabilities. As a result, a bright meteor crossing the sky above the Mississippi River naturally attracts attention because it appears unusual and dramatic. Human psychology often assigns significance to unusual events, especially when they occur near places already associated with danger. The new Madrid Seismic Zone occupies precisely that category. Its reputation stems largely from the earthquake sequence that struck between December of 1811 and February of 1812. Historical accounts describe multiple major earthquakes occurring within a span of just a few months. The sequence altered landscapes, damaged settlements, and generated effects that were reported across vast distances. Population density during that era was relatively low compared to modern standards. Even so, the earthquakes left a lasting impression on those who experienced them. Had similar events occurred today, the consequences would have been substantially greater simply because many more people now live and work throughout the central United States. Major transportation routes cross the region, rail networks, interstate highways, pipelines, power transmission systems, river infrastructure, and numerous urban centers occupy areas that were sparsely populated during the early 19th century. Consequently, the new Madrid Seismic Zone remains a subject of continuing interest, not because a major earthquake is expected tomorrow, but because the potential impacts of future large events could be significant. Against that backdrop, the June fireball served as a reminder of how quickly public attention can focus on the intersection of astronomy and geology. Fireballs themselves are extraordinary examples of energy in motion. Many enter Earth's atmosphere traveling at speeds exceeding 25,000 miles per hour, or more than 40,000 kilometers per hour. Some travel much faster. At such velocities, even relatively small objects can produce dazzling displays visible across enormous distances. The atmosphere acts as Earth's protective shield. Most incoming objects are destroyed long before reaching the surface. The brilliant light observers witness is actually evidence of that protective process at work. Material from space is being heated, fragmented, and ultimately consumed as it encounters increasingly dense layers of air. For observers scattered across 18 states, the June 14th event lasted only moments. Yet those moments generated thousands of discussions and renewed interest in one of America's most famous fault systems.